Okay, so far this unit we've talked about the concept of momentum, the concept of how to calculate change in momentum and what impulse is, and then the impulse momentum theorem, which basically connects those two concepts. And so just to kind of recap, the impulse momentum theorem basically says that the impulse on an object is equal to the change in momentum of that object. Now, the impulse can also be calculated based off of the force acting on the object in the time that the force acts. But the equation we've seen so far, I equals F delta T for impulse, has a very crucial limitation. This equation is only valid provided that the force acting on the object is constant. However, in real life, it's not actually constant, and if the force is not constant, then typically you need calculus in order to determine the impulse. Okay, and so since this is not a calculus-based class, we're not going to worry about that. And so now we're going to turn to looking at impulse in from a different perspective. Um, that will allow us to be able to solve problems with impulse and with the impulse momentum theorem if the force is not constant. Okay, so not using this equation, obviously, because this equation only works if the force is constant. And so what we're going to look at today is force time graphs. All right, so let's go to the next slide. Okay, so a force time graph is exactly what it sounds like. It is basically a graph showing you how the force on an object, so let's say this is F, measured in newtons, measures as a function of time measured in seconds. Okay, and so you can use force time graphs to, or I should say, force time graphs can be drawn or created to show how force acting on an object changes with time. And so those could be drawn by hand, or nowadays we have sensors or probes that can measure force as a function of time. We actually have some in my classroom that we can use with Logger Pro. But force time graphs can be created to show how force acts on an object and how that force acts change or how that force acting changes over time. Okay, so we've seen time graphs before when we did motion graphs. So we saw displacement time graphs, velocity time graphs, and acceleration time graphs. And as we learned about at that point, sometimes looking at the slope of the graph or the area under the graph can give us more information about certain quantities. Okay, and so that's also true when it comes to force time graphs. And so here it is, I put it in bold. This is the key part you need to know about force time graphs, is that the impulse can be calculated from a force time graph from the area under the force time graph. Okay, now let me say that one more time. The area under force time graph represents the impulse, aka the change in momentum of an object. Now, that statement is true even if the force is not constant. Okay, so this idea allows us to use force time graphs to calculate the impulse if the force is not constant. Obviously, if the force is constant, we could just, use the impulse equation and there'd be no issues. But if the force is not constant, then that equation no longer holds. Okay, but this thing I just put a box around, the area under the force time graph representing the impulse, that's true, no matter whether the force is constant or not. Now, I will say, just for the sake of completeness, that at this level of your mathematical career, since most of you probably don't know calculus, you can probably only find the area of simple shapes like triangles or rectangles or squares. And if you had a graph, let's say you had a graph that looks something like this, and I asked you to find the area of that type of curve, you probably couldn't do that because that would require calculus. And so you're not going to see any shapes like that. Most likely you would see shapes involving squares and rectangles and triangles like we've seen before in the past. Okay, but this idea that I put the box around is still true. Even if you don't know how to geometrically find the area, that statement is still true. Now, when I say the area under a graph, what I mean is the area bounded between the graph itself and the x-axis. Okay, and so in other words, let's say you had a graph. Let's say this is a force time graph like this. Let's say I gave you a graph like this, and I asked you to find the area under the graph, what I would mean in that situation is the area between the graph itself and the x-axis. Okay, so the area bounded by between the graph and the x-axis. And if you go below the x-axis, you can actually have negative area. And so this blue quantity right here, you would count that as the negative area. Okay, so you can have positive or negative quantities when you're finding the area under a graph. And so the impulse on an object, and hence the area under a force time graph, can be a positive or negative quantity because impulse is a vector and so it has direction. Now, obviously here I've drawn curves, and so I said before you wouldn't be asked to find the area of curves, but the principle is still true. So when we talk about area under a graph, we don't mean like literally like all the way under a graph. We just mean between the graph itself and the x-axis. All right, so um, pause there, make sure you add that to your notes, and then we'll just do some quick examples. Okay, so let's take a look at example 1. So example 1 says, the force time graph shown to the right shows the force acting on a tennis ball as it bounces off of a wall. And so let's say tennis ball is flying through the air, there's no force acting on it, but as soon as it comes into contact with a wall, let's say right here, it begins to experience a force, and that force is not constant, because actually what's going to happen is the tennis ball is going to compress against the wall, and then it's going to be shot back out. Okay, but the direction of the force, which in this case I guess would be the normal force from the wall, would always be pointing perpendicular to the surface. And so that's why you see from this graph that the force actually never becomes negative. It's positive the whole time. It just increases, reaches a maximum value, and then decreases again. Okay, and so here where the red dot is, that's where the tennis ball hits the wall and then it compresses and gets shot back out. And so right here where the force goes back to 0, that's where it leaves the wall and it's no longer touching the wall because, well, if it's not touching the wall anymore, that's why the force goes to 0. Okay, so the first question says, determine the change in momentum of the ball. Now, obviously, we're going to use the concept that we just learned about, which is the area under a force time graph represents the impulse acting on an object. Okay, and because of the impulse momentum theorem, we know that impulse is equal to change in momentum. And so when it says determine the change in momentum of the ball, we can also interpret that as calculate the impulse acting on the ball, aka find the area under this graph. And so that area would be the area bounded between the graph and the x-axis. And so I guess I will do that in green. Okay, so that would be this area right here. And this is like a triangle. Okay, and so we can find the area of a triangle doing 1/2 base times height. And so here the base would be 0.5 seconds. Do make sure you pay close attention to the units because sometimes you'll have problems where, this could be in like meganewtons or kilonewtons or something, or this could be in milliseconds or microseconds. So do pay attention to the units on your graph. But in this case, we're in seconds. And then the height would be 150 newtons. And so if I do that calculation, I get 37.5 Newton seconds. And so that is the impulse, aka the change in momentum of the ball. Okay, by the way, notice the unit for impulse is Newton seconds because again, what we're multiplying is 150 newtons times 0.5 seconds. So that's where the Newton seconds comes from. Okay, so that is the answer to the first question, 37.5 Newton seconds. Now the second question says, if the ball has a mass of 0.5 kilograms, estimate the velocity of the ball right before it hits the wall. Now this is kind of a tricky question, okay? And so there's a couple different ways to think about this question. But let's think of it like this. I'm going to erase this area right here. Okay, so it hits the ball at the red dot, and then the ball is going to compress, the force is going to increase. If you had to guess, what point on the graph do you think it begins to change direction and go backwards? Okay, well, in my mind, that probably happens at the middle. Okay, so at the red dot is when it first touches the wall, that force is going to increase, and then right here, the force reaches a peak and begins to decrease again. And so what's happening over here is the ball is starting to rebound in the opposite direction. Okay. What that means is where at this time where I put this black dot, at that time, most likely the tennis ball is at rest. Okay, so it hits the wall, it comes to a stop for a split second, and then gets shot back away from the wall. Okay, now that kind of requires some abstract thinking, and so this example one is not necessarily the easiest example to start with, but it is what it is. And so basically what I'm saying is at time 0.25 seconds, the ball is at rest. And so what we can do is we can use that to estimate the velocity of the ball right before it hits the wall using that time. Because we don't know VI, but at that one time, we can say that VF is equal to 0, right? We also know that the area of this first triangle right here represents the change in momentum, which is mv final minus mv initial. On the right side, I know the mass is 0.5. I know v final is 0. And this is 0.5 times vi, which I don't know. On the left side, that should equal the area of this triangle right here. Okay, the first half of that triangle, which coincidentally would be half of the area I found before. In other words, it would be 1/2 times 0.25 times 150, okay, which is going to end up being the same as half of 37.5, which is going to be 18.75. And so on the left side, the area under the graph represents the change in momentum, and that area is 18.75. And so I can use that to solve for VI. That's going to be 0, 0 minus 0.5 VI, and then all I need to do is divide both sides by 0.5, and I get VI equals negative 37.5 meters per second. Maybe not realistic for a tennis ball, but that is what it is. Now you could say, why is it negative? Well, if you look at the force time graph, the force acting on the tennis ball is acting in the positive direction. You can see that from the graph. Well, what that means is that originally the tennis ball must be moving in the negative direction, then it hits the wall, and the force, which makes the tennis ball rebound, is acting in the opposite direction of motion. All right, so that is example one. Pause there if you need to look at that some more. All right, let's just look at one more quick example. All right, example 2. It says the force time graph shown to the right shows the force acting on a 1.5 kilogram particle. Assuming the particle initially is traveling with a velocity of 5 meters per second, calculate the velocity of the particle after 5 seconds. Okay, so we're using the same concept here, the impulse momentum theorem, but we're going to use the area under the graph to find the impulse. Sorry, impulse is equal to change in momentum. I can't use that equation, by the way, to find the impulse because you can see the force is not constant during the first 3 seconds. Okay, so I need the impulse. I want the velocity of the particle after 5 seconds, meaning, not literally after 5 seconds. What I mean is like, at 5 seconds, basically. After 5 seconds have passed since the beginning of the problem, which means at 5 seconds. Okay, so I equals delta P, and delta P is mv final, which I don't know v final, that's my unknown, minus mv initial. So I have the mass, I have v final, and I have the initial velocity is 5. And then I just need to use the area under the graph to find what goes on the left, okay? Because the area under the graph represents the impulse. All right, so pause there and see if you can finish answering this question on your own. Okay, so I've got two areas actually. I've got this triangle here, which I will shade in red. I've got that area, and then I've got this rectangle right here, which I will do in blue. Okay, and so just to do the blue one first, that is just like a rectangle, I guess. And so the area of the blue one would be base times height, and so that would be 2 from 3 to 5 is 2, times the height, which would be, let's see, -4. And so that would be -8 Newton seconds. Notice it's negative because the height, aka the force, is negative. Plus it's under the graph. The area of the red triangle would be 1/2 base, which is 3, times the height, which is 6, and that would be 9. And so if you get 9 plus -8, that gives you 1. And so that means the impulse acting on this particle over the entire time is 1. And now all I have to do is rearrange this and get VF by itself. Okay, so 5 times 1.5 is, let's see, 7.5. I would add that to both sides, plus 7.5 plus 7.5, boop. So I get 8.5 equals 1.5 VF, and then I divide both sides by 1.5. Okay, so 8.5 divided by 1.5. I think I typed that in wrong. VF equals 5.7 meters per second. Okay, and that is the answer to the question. Now, again, when you're doing these forced time graph problems, make sure you pay close attention to the units. Here, the y-axis was already in newtons, and the x-axis was already in seconds, but it's not always going to be that case. Also, pay close attention to where you are asked to find the velocity, because here it says find the velocity of the particle after 5 seconds. But let's say the problem said, how fast is the particle moving after 2 seconds? Well, if it said after 2 seconds, then we would have only been concerned with the area between 0 seconds and 2 seconds. And so that would be this area right here, which is kind of like awkward because it's like part of a triangle. But then we would only be using this area right here to answer the question. Okay, now in this case, we are asked 5 seconds, which is basically the entire graph, but that's not always going to be the case. So that is how you solve problems using forced time graphs, and that's generally how you solve problems involving impulse where the force is not constant. All right, so um, as always, please let me know if you have any questions, and I'll see you guys in the next video.